Okay, so let's work with some more potential and energy type stuff here a little bit. We're going to start something a little pretty basic. Here we go. We got a positive charge over here. Let's say this is an 86 nanocoulomb charge. And let's say that 46 micrometers away, well, let's use a proton. We've got a proton over here. And what it's going to do is, well, it's going to start rest here, so no big deal. And then what it's going to do is going to, of course, be repelled. We did a question similar to this before. And let's say over here it's going 3.63 times 10 to the 7 meters per second. And we want to find out how far did it go. So we'll look for that. And let's also find out what was the average force that was used to actually move it. Okay, now big clue here, radius is changing. We have a changing radius, the distance is changing. So this is all about one thing. This is all about NRGs, all about energies. So let's just find our energies as best we can and see what we can do. All right, so over here, we have got potential energy. So I'm going to find out my potential energy. So that's K, Q, Q over R. So I can start with that and find out how much potential energy it started with. So if I do that, I should get around 2.69 times 10 to the negative 12 joules. All right. Well, I've also got that speed up there. And with that speed, and I know its mass, I can find out how much kinetic energy it had. So the kinetic energy over here, 1/2 mv squared, I can calculate how much kinetic energy it had. So if I do the 1/2, get the mass of a proton, multiply it by the speed squared, we've got about 1.1 times 10 to the negative 12 joules of kinetic energy. All right, so this is how much energy it started with, and then it went further away and got this much kinetic energy. Now, it's all about changing energies. All the changing energies are going to be equal to each other. So the potential energy was this, and as the proton moved further away, the potential energy is going to get smaller, and it's going to get smaller by the change in kinetic energy. So if I subtract those two, I can find out my new potential energy has to be the difference between the two. So if I subtract those two, I can find out my new potential energy, which would be around 1.59 times 10 to the negative 12 joules. So that's the potential energy at this location. All right, well, now that I have the new potential energy, I can find out the new radius, because that's just equal to KQQ over radius 2. And then we can use that to solve for our second radius. All right, so if we solve for that second radius, should be about 7.8 times 10 to the negative 5 meters, or like 78 micrometers. All right, but that's the radius from the initial big positive charge. But I want to know how far it went. Well, the initial radius was 46. So I started at 46. The new radius is 78. So all I have to do is subtract the two, and I can see that it must have went, just subtract the two, no big deal. And we've got about 32 micrometers. So the proton went about 32 micrometers to go from one place to the other place. All right, so next we're looking for the average force that was used. All right, now it's all about energies. And this was the change of potential. It was the change of kinetic energy. It was also the work done. So average force is just work divided by distance. So there's my work right there. The distance I'd want to use is that, the one that it actually traveled. So if I divide those two out, I get an average force of around 3.4 times 10 to the negative 8 newtons. All right, so there is my average force. Let's clean up that 8 a little bit. That's a little better. Okay, something like that. Okay, so again, very similar to what you guys did with gravity. Okay, so let's see what we can do with this. And actually, we know we're going to also connect this to the electric and the forces type stuff as a little bit as well, and see what happens when we got a little bit of a combo charge type situation going on. But I'm going to show you guys something else first along these same ideas though. Okay, and I'll show you why that change in energy thing is so unbelievably important. Okay, suppose you had two positive charges like this, and you had a proton right in the middle. Okay, and the two big positive charges are equal to each other. That proton in the middle has got huge potential energy. If you actually calculated it, it'd be K QQ over R, be K QQ over R, and you'd add those two energies together and you would have huge potential energy. But it's not going anywhere. Okay, it'd be locked in between it with equal forces and stuff like that. It's locked, it can't move. Things don't move because they have energy. Things move because their energy can change. That proton's energy can't change. Since it can't change, it's not going to move. Okay, suppose this was 5 joules and this was 5 joules. Well, this thing's got 10 joules of potential energy, but it can't go anywhere. Okay, now what if instead this was a negative charge? Okay, well then this would be negative 5 joules. Well, the 5 plus the negative 5 is 0. It would have 0 joules of potential energy. But this proton is going to move towards the right at probably incredible speeds because its potential energy can change. It's not about how much energy you have. It's got 0 joules of potential energy. It's the fact that its energy can change. So it's all about the change in energy for these things. That's the key for this type of thing, whether it's gravity or subatomics, it doesn't matter. It's all about your energy changing. Okay, it's sort of like being on a deserted island. So here you are, you're on a deserted island, all surrounded by waters and stuff like that. And you've got a tree, there you go, there's a little palm tree for you, blah, 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 blah. And here you are, sitting here, there you go, all sad and droopy. And you've got stacks of cash. You've got millions and millions and millions and millions of dollars there, even billions if you want. That money is absolutely useless. Money is no good unless you can actually use it for something. Unless you can actually change the amount of money you have, it doesn't matter if you have it or not. Same thing for these joules. Joules, it doesn't matter how many joules you have. It doesn't matter how many dollars you have. It's all about how much your energy can change. It's all about how much money you can change by buying stuff. Okay, so that's sort of the key idea behind this type of stuff. Okay, as long as your energy doesn't change, you're just keeping the same potential energy. It all sort of ties together. Okay, that's why if we take a nucleus and we talk about the electron orbiting the nucleus, as the electron orbits the nucleus, its potential energy never changes. The Q's don't change, the radius doesn't change, blah, blah, blah. So as that electron orbits around the positive and orbits around the nucleus, its potential energy never changes. Since its potential energy never changes, there's no work required to go around. That's why electrons can orbit and orbit and orbit and orbit, and you don't have to introduce energy to let them keep going around. Since their potential energy never changes, there is no work required for them to go around. Okay, so that's kind of a neat application in terms of orbits and how these things sort of kick in. When you do actually modify this a little bit, there are different electron orbits, of course, and if you have a higher orbit and that electron jumps to a higher orbit, that requires energy because you've changed the potential energy. So you change the potential energy as the electron will jump between shells. And of course, if an electron jumps up into a shell, it has a change in energy. Of course, they're often unstable and eventually they will fall back down. But when they fall back down, there's a change in energy. And that's often when you have light being given off. And that's where spectral lines come from in spectral analysis for atoms, is when electrons jump between different shells and change their energy, and when they fall back down, there's different amounts of energy which gives off different amounts of color depending on the atomic structure and the distance they fall down and that type of stuff. So that's where spectral lines come from when you look at spectral analysis for different elements. You guys looked at that in grade 9 science a little bit. This is where that type of stuff kicks in. So it's always about the change in energy. Again, not how much energy you have, it's about how your energy changes. And like an atomic structure type idea, that change in energy is what gives you your spectral lines. Okay, so maybe you had another orbit, maybe over here. Oops, that should be black. Another orbit over here. Well, if that electron jumps up all the way over here, if it falls all the way back down, it will give off a certain color as it falls all the way back down. But maybe that electron instead, fell down here and then down here. Well, then it would give off two different colors. One color when it fell down the first part, and then a second color when it fell down the second part. So this is why you get different colors of bands depending on how the electrons fall back down to their stable orbits. And it's all about changing their potential energy. Okay, so this is one of the key things. You have the electric fields and you've got the forces for pushing things around, but the electric potential and potential energy kicks in for analyzing the energies and the, what changing the orbits of electrons, atomic structure. It all sort of ties together. Okay, so we'll be doing some more practice with electric potential and energy and moving charges around a little bit.